In this lesson, we show how RSA asymmetric algorithm based on Euler-Toten theorem. And we show how the public key and private key are generated, and we also describe how the message is encrypted and then decrypted. We apply the Euler-Toten theorem to prove that the resulting operation recovers the original plaintext messages. RSA is a symmetric crypto algorithm proposed at 1978 in a paper by Ron Vivest, Adi Shamir, and Len Edelman at MIT. The name of the algorithm is the initial of the last names of the three inventors. It is an exponential cipher utilized Euler's Toten theorem. It is also called public key cryptography, where the public key is given out to everyone to use and the private key is kept by the creator of the key pair. It is based on the fact that finding factors of a large integer is very difficult, very hard, and is called the factoring problem. For their work, they received the prestigious 2002 ACM Turing Award, considered the Nobel Prize of Computer Science. RSA key generations is a 5-step process. First, we choose the two large random prime number, P and Q. They are different. Compute n equal to P times Q. And it's called the modulus for the public key and the private key. Third, we calculate the total phi of n, which is equal to P minus 1 times Q minus 1. Fourth, we choose the integer e such that it is between 1 and phi of n, total function of n. E is relative prime to phi of n, and then the E is released, send it out to everyone as a public key exponent. And often the 65537, which is 2 to the power of 2 to the power of 4 plus 1. And here we use a formula 2 to the power of n plus 1, where n equals 4. And this formula is called formula number. And with n equal to 4, we call formula number 4, or F4 in short. And typically we use this number as E. Compute D such that D times E is equal to D times E and 1 are concurrent of phi of n, or using the equal operator, D times E is equal to 1 times some k multiply phi of n. D is kept as a private key component, and the public key is, in this case, the two tuple, E and N. The private key is the tuple D and N. Let's now show how RSA do the encryption and do the decryption. And here we have big message like M. We typically chop them into small message segment or chunk called little case, represented by little case m. And through the equation, we can compute the C, little case c, which is ciphertext, and n is the modular here, E is a public key exponent, D is a private key exponent. So let's look at the encryption process. Let's say artists like to give, in the first step, give out the public key E and N tuple to Bob. Bob then chopped his message, the message he tried to send to Alice, into a small chunk. Each of them is a number smaller than m. The smaller than n, the modular. And let's represent that small chunk as little case m. Bob then compute the ciphertext C with m to the power of e modulo n. The formula we use here is C equal to small m to the power e modulo n. And so what we are saying is C and m to the e is congruent modulo n. And then with the C computed, Bob sends C to Alice. Now let's look at the decryption process. The Alice will first receive this M receive C from Bob, and he can recover M from C by doing this formula, which is C to the power of D modulo n. And because we know the little original message m, little case m, and the c to the power d are congruent modulo n. Okay, now let's try to prove why that's the case. The last formula. So here is a proof of RSA algorithm with the message applied to the power of public key exponent with the modulo n operation, followed by applying that to the power of private key exponent modulo n, we will recover the original message. Step 1, let's prove it. We use the fact that the formula ed and 1 are congruent modular of phi of n, the total function of n. It holds true based on the IS key selection method, how they select D. It is then extended to these two equations here hold true, where E times D and 1 are congruent modular of P minus 1 and modular of Q minus 1, since phi of m is equal to P minus 1 times Q minus 1. Step 2, we apply format little theorems, and m to the power ed is then congruent with m on modular p and modular q. Step 3, since p and q are distinct prime number, apply the Chinese remainder theorem, which we are going to cover in specialization of applied cryptography taught by Dr. Sam Yong. To these two groups, we can then derive m to the power ed and m are congruent modular of p and q. Therefore, c times d and m are congruent modular n. This concludes the proof. Here we illustrate with small number on using RSA for confidentiality purpose. First, we show encryption using Alice public key. Let's P equal to 7, Q equal to 11, and P times Q is 77, so n, the modular n is 77. And phi of n with totem function of n is 60, because based on the totem function property is equal to 7 minus 1 times 11 minus 1, 60. Alice then choose E, 17, which has to be the relative prime number to 60, totem of 77, which is 60. It then find the private key D. And we find out when D is equal to 53, it satisfies the equation E times D mod phi of n equal to 1. And we can plug in 17 times 53 is 901. And if we do a mod 60, it happens to be 1. If we represent the alphabet, all uppercases, and the blank with number 0 represent 8, 7 represent H, 25 represent Z, 26 represent blank, then the hello world can be encoded with a single digit like 7, 4, 11, 11, 14, 26, 22, 14, 17, 11, and 3. Okay, and Alice would then announce its public key, the two tuple E and N, which in this case is 17 for E, 77 for N. Send it to Bob in public channel. Using Alice's public key, Bob can generate the following ciphertext. 17, which is h to the power of 17, which is the public key of Alice, and then mod 77, which is a modular equal to 28. And same thing here, 4 to the power of 17 mod 77 is 16. And so on until the last number 3 times to the power of 17 mod 77 is 75. So Bob then sent all these encrypted number 28, 16, 44 all the way to 75 to Alice. Only Alice has a private key. Only he can decipher messages. Now let's look at the decryption process. First, Alice's public key is E and N, which is 17 and 77. The private key corresponding to that is D and N, which is 53 to be D and N is 77. So we have this E times D mod phi of N equal to 1, and 17 times 53 mod 60 equal to 1. So since Alice received this encrypted number from Bob, 28, 16, 44, 75, we are going to use the private key, 53 and 77 to decrypt that. 28, first number to the power of private key D, 53. Mod 77 is 7. Indeed, we recover 7, which is H. 16 to the power of 53 mod 77, we can compute that value and happen to be 4, which is E. 44 times 53 mod 77 is 11, that happen to be L. And so on until 75 to the power of 53 mod 77, we got 3, that happen to be D. So Alice was able to recover hello world messages. On the Mac or Linux machine, you can actually using a utility called BC to compute these values. It is shown with in the light green box how the computation result using the BC or all these calculation, decrypt calculation. RSA, we try to apply that for authenticate the origin. Alice computes the message using Alice's private key. Alice's public key is 17 and 77. Private key is 53 and 77. Here, Alice would like to send a message to Bob, actually for anyone, and let him know this message sent indeed by her. And so the purpose is authentication. We are not intend to hide the messages. No need to encrypt here. Alice using her private key to compute the messages, and anyone can use the public key, her public key, to prove the message was indeed sent by her. Let's use hello world, the encrypt code. 7 to the power of private key of Alice 53 mod 77 is 35. 4 times to the power of 53 and mod 77 is 9, and so on until 3 to the power of 53 mod 77 is 5. So Alice will send 35, 9, 44, 5 to send it to Bob. Bob can apply her public key and recover exactly the messages. And all this cannot be sent by anyone but her, because only she owns the private key. Here we show the scenario where the message is encrypted and authenticated, both. And Alice, in this case, Alice encrypt using Alice's private key first, and then and the order matter here. And then the result is encrypted using the recipient, the Bob's public key. And the Bob's public key is 37, and the modular n is 77, and the public key is 10 and 77. Alice's public key is 17, the modular n is 77, and private key 53, and with a modular n 77. Okay, let's look at how Alice do the encryption. First, he takes the original message data 7 to the power of 53 more 77. And the result applied to the power of 37, which is Bob's public key exponent and mod 77. The result is 7. And then same thing for 4 and 11, and finally 3 to the power of 53 mod 77 to the power of 37. Mod 77 is 47. Right? So all this number is sent to the Bob. Let's look at how Bob do the decryption decipherment. And it's going to use its own private key, because the last step Alice do is using the Bob's public key to encrypt it. Therefore, we need to do a reverse process. Okay, so we receive 7, take to the power of Bob's private key, which is 13 mod 77, and the result we then apply to the power of the Alice public key exponent, which is 17 mod 77, and we recover the result is 7. And same thing for 37, goes through the same formula, we get 4. And 47, we apply the same formula, we get 3. And indeed, we have this received message that is both encrypted, and we can provide authentication based on the other side's public key. Only the sender can do the encryption using their private key. Only Bob can decrypt his private key and recover these encrypted messages. And Bob can then apply Alice's public key to ensure the message indeed sent by him using Alice's private key for authentication purpose inside.